Taylor series. In this session, I will talk about the Taylor series. That's what it is. First of all, Taylor series is a power series. And we did study, yes, the study of the power, we did study a power series. The study of the power series is largely about taking non-polynomial function and finding a polynomial that approximate this function near some input. Of course, we have to think always about the center, interval of convergence, radius of convergence. And that's why we did this. And one of the main formula that we were working on was 1 over 1 minus x can be represented as a power series summation x to the power of n from 0 to infinity. And when we expand this, x to the power of 0, x to the power of 1, x to the power of 2, 3, and so on. And this is good only on that interval. And that's we remember this was our strong tool, of course, based on the geometric property. And we were taking this rational function and we were trying to find the power series representation. If the function looks similar, was easy. Some of the functions were not exactly similar, but using some differentiation, integration, we were still managed to use this tool to get the power series. And just one more thing to say why we're doing this, because polynomials are the easiest function. I mean, much easier to deal with than the other functions. Easy to compute, we can see easy to find the derivative, just the power form, integral, and just easier to solve lots of problems. And that's this is the main motive that we're doing this. Okay. That's what we have to do. We definitely have to extend this process of finding power series representation for more function, for more non-polynomial functions, not just this rational function. Okay, that's we can see this is the formula. Oh, one more thing. Let's say this, it's really important. We start by supposing that f is any function that can be represented by the power series. That's one more comment. Not all of the functions can have power series representation, but in this class, in this video, we will definitely talk about the function that, yes, they can have power series representation. And in general, really broadly, the name of these functions, this is the type of the function, and the type is called analytic function. That means all of the analytic functions can have power series representation. And that's why we will definitely look at the functions that, yes, they have power series representation. Okay, now we can start. This is the general form, of course, of the power series. C sub n, coefficient x minus a. A is the center of the interval of convergence to the power of n, and that's the expanded form. And we may also notice x to the power of 1, x to the power of 2, x to the power of 3. This will define a degree of this polynomial if we decided to just stop at some point. But in general, we're talking about the series, talking about the nth degree polynomial. If, of course, we have convergence. Okay, that's what we will do. We have to find a general way, because as I said, this is not enough. We will try, because this part, x minus a to the power of n, always stays. Yep, doesn't matter what is the function, we always have this component, this factor of the product. But what is different is the coefficient c sub n. So we will try to connect through some formulas coefficient c sub n with the given function. Because if we can get the formula for the coefficient c sub n in terms of f, then we can take any analytic function and find the coefficient with respectively to the function, and then we will have a power series representation. Excellent. Let's start. Yes, let's try to determine the coefficient c sub n. First of all, we will try to look at what is happening at the center A. That's when we will put to this equation, to this expansion. Instead of x, I will substitute a. That means a minus a, 0, 0, 0, 0. That means f of a will be just a constant c sub 0. Okay, that means we can see we have a nice connection. F of a is c sub 0, always. So nice. Okay, that means now let's keep moving. F of a, c sub 0. Now I will try to take the first derivative. It means taking derivative of this expanded form is not a problem because it's just a derivative of the power function. X to the power of 1. We have a coefficient constant c sub 1. That means derivative of c sub 1 x is just c sub 1. Derivative of c sub 2 x squared, it will be 2 times c sub 2 x. And of course, we have to carry minus a. C sub 3x cubed will be 3 c sub 3x to the power of 2, and so on. Yeah? Of course, derivative of the constant, 0. That means this is the derivative, c sub 1, 2 times c sub 2x, 3 c sub 3x squared, x minus a. Because derivative of the inner function is 1, that means we also follow the chain rule. 4x cubed, 5x to the power of 4. And now we will try to do the same. I will replace x with a. That means if I will replace x with a, finding the value of the derivative at a, this is 0, 0, 0, 0, c sub 1. We will get c sub 1. Okay, let's repeat this process. Let's find the second derivative of this line. Okay, that means I don't have to explain. You can maybe pause the video and look at this, but it's just derivative of x will be just the constant, 2c sub 2. Derivative of x squared is 2x, and copy that constant. Derivative of x cubed is 3x squared, x minus a, of course, and copy that original constant for x, for c sub 4, and so on. And then repeating the process, finding the value at a of the second derivative. These terms will be gone. It will be just this one. Okay, that's we can probably, and you probably see me writing this form, c sub 1, in the weird way, 1 times c sub 1, 1 times 2 c sub 2, and then repeating maybe one more time the first derivative, and substituting a, it will be just this term, because all of the others will become 0. 1 times 2 times 3, c sub 3. I mean, you can probably see the pattern. That's the connection. If it's the first derivative, it's 1 times c sub 1. Second derivative at a and the center equals to 1 plus 2 c sub 2. The third derivative at a equals to 1 times 2 times 3 c sub 3. Then the fourth derivative, the fourth derivative, 1 times 2 times 3 times 4 c sub 4. And the nth derivative is just n factorial c sub n, because these quantities, these products are the factorials of 2, 3, 4, and so on. That means this boxed formula is the formula that will help us to find the power series representation for almost all of the functions, of course, analytic function. Okay, that means this is the formula. And the because when we are, one more, let me come back. That's mean when we actually solve this for the coefficient, yes, c sub n will be, this represents the derivative, nth derivative. That means this is the nth derivative at the center a over n factorial. Okay, nth derivative at a over n factorial. And just a small comment, if it's, yes, 0 factorial is, because 0 means just the function. If this will be 0, if n is 0, we just thinking function, value of the function at a. And 0 factorial is 1. We remember this. Okay, so now let's look at a couple of theoretical slides and we will do the exercise. Power series, yes, and now when we will replace the coefficient c sub n with this formula that we actually found, we will get this form. And since this formula was on this formula, worked one of the English mathematician, Brooke Taylor, we will call that this is the Taylor series. Taylor series. If we see this formula, Taylor series centered at A. Okay, and then we also have a special case of a Taylor series, which is always centered at 0. And when we have this, we can see I just replace A with 0. Then this one, yes, is called actually Maclaurin series, because one of the Scottish mathematicians worked on that form. Okay, but it's basically still a Taylor series centered at 0. We can say this, or we can say Maclaurin series, then we will know that this is the center is 0. Okay, so now let's look at this. In general, we can say that function f of x is the sum of a Taylor series, and that's the formula, nth derivative n factorial x minus a to the power of n, and we may split this for the partial sum and the remainder. Partial sum in this case is called nth degree Taylor polynomial, because we will stop at n, and n actually will be the degree of this polynomial. That means the nth degree Taylor polynomial plus the remainder. And now, there is no guarantee that the Taylor series, T sub x, Taylor series converges to the function, even if the series converges. What is important? The Taylor series converges to the function f of x if and only if that remainder goes to 0 at infinity. Okay, that's important. Now look at this. Let's look at this again as a theorem. If function, yes, is defined as a theoretically Taylor series, that means Taylor, the partial sum, if we take just a couple of terms, nth term, we call nth degree Taylor polynomial plus the remainder. And if this remainder eventually goes to 0, then yes, f is equal to the sum of its Taylor series. And we may write this. Of course, at a certain point, n x minus a is less than r is the interval, the radius of convergence, and solution of this will provide an interval of convergence. And just the small comments, in general, this is not easy to prove that this remainder goes to 0, but we will assume that all of the examples that we're doing, the remainder goes to 0, and the function is equal to the sum of its Taylor series. Okay, now let's work on a couple of formulas. We have to really practice this Taylor formulas, the nth derivative at a over n factorial. Okay, that means the first function is e to the x. Find the Maclaurin series of the function e to the x and its radius of convergence. That means this is function e to the x. That's the general formula. We can see 0 because Maclaurin, we know automatically that the center is 0. And this is the expanded form. F of 0 plus f prime over 1 factorial x to the power of 1. F, the second derivative at 0 over 2 factorial x to the power of 2. Plus third derivative over 3 factorial x to the power of 3, and so on. And I just built the table for a little bit easier, just at the beginning, of course, a little bit easier, because what we have to do, we have to find out all of these coefficients. That means f of x, if we can see the first column represents the derivative. 0 means just the function. First derivative of the function is e to the x. Second derivative, third derivative, fourth derivative. That means this is a nice, easy example because the nth derivative of the function e to the x is e to the x. Now at 0, it will be 1. It will be basically 1. That means the nth derivative at 0 is 1. Yes, not all of the functions will have a nice pattern. And I don't know if we really need the last column, because the last column is just these coefficients. Yeah? We may say this will be 1, this will be 1, this will be 1/2, and this will be 1 over n factorial. So we can write, I can write this, too fast. No. I mean, I can write this formula that e to the x, okay, the nth derivative, or maybe this one, the nth derivative at 0 is 1 over n factorial, and then x to the power of n. That means this is the formula that we need. Okay, we also have to find out when we can use for what axis, what is the domain, but you can use, we remember, in order to find the interval of convergence or radius of convergence, you can use the ratio test, and you can try. I have the solution on the next slide because we did practice this a lot. That means I can just tell you that yes, this will be good for all of the numbers. Okay, and this is the formula. And if we will expand, that means this will be 1 plus 1x, I don't have to write 1, plus 1/2 x squared plus 1/6 x cubed plus 1/24 x to the power of 4 factorials, and so on. So we can see function e to the x can be approximated by this. In the next session, we will talk about the polynomials. That means we will stop at some point and we can even draw. You can even use for instance, Desmos now. You can plot function e to the x and maybe the 4th degree, maybe the 3rd degree, and you can see how nicely they match. Near 0, of course, near 0. Okay, that means this is the first formula to remember. E to the x equals to 1 over n factorial x to the n summation, of course. Okay, and I have the solution. Okay, interval of convergence. Exercise number 2. Now we can practice this just finding the sum of the following: 1, 2, 3, 4, and 5. So we can see this is just e to the x. Yes, e to the x. Because, well, let me come back. Did I say? Yes, because we can see that x to the power of n can sit on the top. Yeah, that means 1 over n factorial, x to the power of n. Basically, x to the power of n over n factorial. Okay, that means x to the power of n over n factorial, important formula to remember. And that's our tool, because when we will see something similar, like this one, we can say, oh, this is 1 to the power of n, e to the power of 1, just e. That means 1 over n factorial is actually equals to e. We remember we were using maybe ratio test to prove that this infinite series is convergent, but we will be not able to find the sum. Now we know. This one looks like e to the negative 1. 1 over e, because it's negative 1 to the n. We're just replacing that x. Yes. This one looks like e squared. And this one, maybe it's a little bit tricky because 1 to the power of n, it's also 1. That means I'm trying to force this formula. N factorial in the denominator and quantity to the power of n. E to the power of this quantity, and I can put 1/3. Cube root of e. Beautiful. Nice. And number 5 is a nice exam type question. Okay, that means we know power series representation for e to the x. Okay, now let's find the Taylor series for the function e to the x, but centered at 2. That's we just almost have to shift it. Function is the same, e to the x, e to the x, e to the x, and derivative, and this will be just e squared, right? E squared. That's why I can say that power series representation, it will be the nth derivative is e squared over n factorial and x minus the center. That means this one will be e squared over n factorial. As I said, we don't even have to think about the last column because I think it's helpful, but let's do the expanded form, but we don't have to fill out here. Maybe we can just provide the formula. Okay, centered at 2. Okay, that means this is still e to the x, but if we would like to find some approximation near the value 2 or some calculation near 2, we will use this one instead of the previous one because the previous one was set at 0. Okay, let's maybe expand. Value of the function, of course, is e. Yes, that's value of the function. This is supposed to be plus. And then plus value of the first derivative over 1 factorial, which is still times x minus 2 to the power of 1. And then value of the second derivative, which is still the same, over 2 and x minus 2 to the power of 2, and maybe one more term. Third derivative at 2 over 3 factorial and x minus 2 to the power of 3, and so on. Right? That means also let's make sure that you can expand each term. Okay. And that's the solution. Okay. Now another function. That's we know e to the x because we will collect the Maclaurin formulas. Now the job for us is to find the Maclaurin series, which is Taylor at 0, of the function sine of x and prove it that the radius of convergence is infinity, which is good for all of the x's. Okay, that means function is sine of x. Let's start with the derivative. I mean, derivative of sine of x is cosine of x. Second derivative, which is derivative of cosine, is negative sine of x. Derivative of negative sine of x is negative cosine of x. And derivative of negative cosine is sine of x. That's, we can see it's kind of like a cycle of 4 because we did reach sine and then we will just repeat. This one, I don't know. Yes, it's not easy to find the pattern. But we still don't have to find a pattern for the formula, general formula. We can find the pattern for the value, derivative at 0. That means sine at 0 is 0, cosine at 0 is 1, negative sine at 0 is 0, negative cosine at 0 is negative 1, and 0, and then 1. That means we may notice that every other term is gone. Yes, that means no value. Second derivative will be 0, the fourth derivative will be 0, and so on. Every even derivative is gone. Yeah? And the other one, the odd derivatives, they alternate 1, negative 1, 1, negative 1. Yeah, that means again, it's not easy to put the formula, but let's see. And of course, not even this one. This one is the same, just dividing by n factorial. That's what I did. I put the expanded form for the general formula. This is Maclaurin series for the general function. Now we know, let's see, that this is gone. Function, second derivative, fourth derivative, and so on. Now let's substitute in the first derivative. What was the first derivative? The first derivative at 0 was 1. Okay, that means this is 1. This will be 1. This one will be negative 1. We can see. And then again, alternating sign. 1. That means we do have 1, negative 1, 1, negative 1, and only the odd exponent. That's what we can say. We can say that this is still general, yes, way, way too general. We only denominators, we have 1, 3, 5, 7, 9, and so on. 2n plus 1. 2n plus 1 is the odd number. And x is also raised to the same power. 2n plus 1, 3, 3. 5, 5, yes? And alternation, that means let's see. X is raised to the power of 2n plus 1. 2n plus 1 factorial actually in the denominator, alternation, yes, because the first, and we're starting from 0, because if it's 0, it's x. If it's 1, it's 3, and so on. And then 0 will give us positive the first step. Okay, that's we did look at the pattern, and this is the formula. That's the pattern, that's the formula. Sine of x has the power series representation like this. Summation from 0 to infinity, negative 1 to the n, x over 2n plus 1 over 2n plus 1 factorial. And if we expand this, it will be 1x minus 1 6x cubed plus 1 5 factorial, I think it's 120, x to the power of 5, and so on. Okay, this is the polynomial with infinity many terms, series, sine of x. And if you use the ratio test, you will get that this is convergent for all of them. This works for all of the values of x. We can substitute any value and get some approximation. Of course, this is near 0 will be the good approximation or the representation. Okay, we have another formula. We have e to the x, we have sine of x, and one more for today is cosine of x. That's the formulas. Okay, that's me. Now let's actually find out. Let's stress out. For each of the following series, find the sum or determine that it's convergent. It converges. That means this one we definitely see sine of x. Yes, x to the power of 2n plus 1 over 2n plus 1 factorial, and alternation, negative 1 to the n. And we can nicely see 2n plus 1 factorial, negative 1 to the n, that means everything match. It will be just sine of pi over 3. Sine of 60 degrees, everybody knows that is square root of 3 over 2. Yes, we found the sum. Now, we have alternation, negative 1 to the power of n, 2n plus 1 factorial, and this one, 1 to the power of any number is 1. That means this one will be sine of 1, and we have to leave it like this, because we don't know, it's not the value from the unit circle. That means this will be the final answer for us. And this one is a little bit, we can see, I can rewrite. It's the summation from 0 to infinity, negative 1 to the n. We have the denominator, the desired denominator, 2n plus 1 factorial, and quantity x to the power of 2n plus 1. And we can see square root of 2 over 2. I can put it back and I can write together. This will be sine of square root of 2 over 2. Also, we don't know. Okay, we will leave it like this. Okay. That's a nice practice of the formula sine of x. Okay, another one, cosine of x. That's what we can do. You may definitely try to do the same way to find this power series representation, Maclaurin series, of course, centered at 0, the same way that I did for sine of x. Finding all of the derivatives, finding all of the derivatives at 0, and thinking how they behave. You will probably notice that all of the odd derivatives will be gone because derivative of cosine is sine. Sine at 0 is 0. That means all of the odd numbers, only even will stay. But what I will do, I will take the advantage of differentiation because I know, and you also know, that the cosine of x, derivative of sine of x, that's actually cosine. And we already know the formula for sine. That means we will try to differentiate power series, which is so easy because we can only focus on this. Rest of them are the constant. We may basically copy the constant. As we can see, I copy negative 1 to the n, I copy 2n plus 1 factorial, and I just differentiate x coefficient, and not coefficient, variables. That means this is the derivative. Yes, if you think about the power rule, x to the power of 2n plus 1 is 2n plus 1 times x to the power of 2n plus 1 minus 1. That's it. And we may 1 minus 1 That's we can see only the even powers. And also 2n plus 1 factorial, I can rewrite as a 2n plus 1 times 2n factorial, like the same number. I mean one number one less, which is 2n factorial times 2n plus 1. Like for instance, 7 factorial, I can rewrite one number less factorial times 7. Yes? If I have 100 factorial, I can rewrite 99 factorial, one number less. That means this is one number one less, and times 100. Okay. Okay. And now the cancellation is ready. 2n plus 1, 2n plus 1. And this is the final formula. Looks almost the same because it's the alternation. Yeah, alternation stays. And instead of 2n plus 1, we have 2n even powers, even derivatives. Okay. Also, one thing, when we taking the derivative, we remember we usually are losing one term because derivative of the constant is 0, that we're supposed to start with 1. But let's actually check. This is the expanded form. When we expand sine of x, and we may notice the first term is not constant. That's we're not losing anything. This is fine. We will start from 0 because derivative of x is 1. All of these derivatives, we can see I copy the factorial from the denominator. Power rule was applied in the numerators, and all of the denominators I rewrite as a 3 factorial is 2 factorial times 3, 5 factorial, 4 factorial times 5, and so on. And now the cancellation. Okay, and this is the formula. Perfect. That's we have e to the x, we have sine of x, and we have cosine of x. Okay, and now you may also use the ratio test and prove it. Oh, I didn't do it. That is work for all of the x's. Okay. And because actually sine of x was good for all of the x's, then cosine will be also good. Converges for all of the x's. Okay. It means now, for instance, how we can find the Maclaurin series for something like this, x times cosine of x. Yeah, that's it. Please don't do the process like from the beginning. Let's use the formula. Cosine is Maclaurin series starting from 0, infinity, alternation, x to the power of 2n over 2n factorial. And now that x, I can move here. Yes, I can move it behind the sigma. That means we may remove this one, and the final answer will be summation -1 to the n, x to the power of 2n plus 1, 2n factorial. And seeing 2n factorial in the denominator, we can still think that, okay, even the cosine was involved. Okay, please always look at the denominators. Okay, and let's look at this one. 1, 2, 3, 4. This is, of course, cosine of x because it's alternation, even. Now we have cosine of pi. And cosine of pi is -1. That means this infinite series converges to -1. This one is a little bit tricky. Let's look at this. Because it's -1, that's okay. 2n factorial, that's okay. And I need quantity to the 2n. We have pi and we have 2, because this one is 2 to the 2n. That means this will be cosine of pi over 2. Oh, actually, lots of work, but the sum is 0. Could be 0, could be 0. Okay, and the last one is nothing actually complicated. Cosine of pi over 6 cosine of 30 degrees. Everybody knows that is square root of 3 over 2. Now, please make sure that you can deal with these formulas. And I supposed to have, I have another, because this is the summary, but I have another one. Let's look at this one. This one, it's from the previous, from the previous session, from the previous lecture. It's even, not even, odd exponents, 2n plus 1, 2n plus 1, but in the denominator, we also have 2n plus 1, but we do not have the factorial. And we remember that this is arctangent of x. Yes? And this one is only good between -1 and 1. Okay? Only good between -1 and 1. No, that means I don't know if I can use this one, because 2n plus 1, I was gonna say, okay, arc tangent, because we cannot actually accept 1. That means let's do this, but we will not apply, because it will be not convergent. Some calculations, because we cannot really include 1 or -1. Okay, that means this one. Oh, we can still, okay, let's just leave it. This one will be arc tangent of this is good, because this exercise was just showing that this is not sine, because the factorials, this will be sine of x, sine of the quantity. And this is just for the exercise is good, but we cannot really use that input. Okay, that means this one will be square root of 3 over 3. This one is good. And tangent for what angle is square root of 3 over 3? We know that this is for pi over 6. Okay, that means that will be important. And this one also, I want students to recognize that this is arctangent of square root of 3. Tangent for what angle is square root of 3? 60 degrees, pi over 6. Okay, that means number 2 is tricky. We cannot really use it. Okay, and now this is the summary. Okay, that means that's the summary. That's all of the formulas that we have to know. Okay, the geometric one, rational function, e to the x, sine of x, cosine of x, arctangent, and also this one, a natural log of 1 plus x. This is the same. This is from, actually, we can find this. You can even practice to find this. We did, I think, in the previous session, because this is based on the rational. You may think about the integral of 1 over 1 plus x, and then you can integrate and get this form. Okay, that's me. Now let's finish the session, because I have more examples, but let's finish the session with all of those. That's me. Let's try to find. Let's maybe pi, not pi. Let's put, I know what we can do. Let's do factorial, yes, because this is the same one. Okay, that means what we have. Yes, the first one, since half factorial, it will be sine of 1. And we can leave it like this. This one is no factorial in the denominator, 2n plus 1. Then it will be arc tangent of square root of 3 over 3. We just did it. Tangent for what angle is square root of 3 over 3? Of 30 degrees, pi over 6. This one is again 2n plus 1, 2n plus 1, everything match, factorial, sine of pi over 3. Sine of 60 is square root of 3 over 2. We know the unit circle. Okay, this one is interesting. This one is interesting because this one has, okay, that means this, it's the natural log of 1 plus x. Yeah, because the denominator, I always look at the denominators, n factorial, 2n plus 1 factorial, 2n factorial, 2n plus 1 only, and n. Okay, that's how we can maybe force to memorize. And this one has no fraction. Okay, that means I see n, then I will, let's actually match, starting with 1, -1, and -1. And then quantity x to the power of n over n, right? We can see x to the n. And then it will be natural log 1 plus x. Natural log 1 plus that quantity. And if this, I can force it, I can put 1 to the n. It is 1 to the n over 2 to the n, 1/2. 1/2. And this will be natural log of 3/2. And this is good because this is only good, again, between, for all of the x's, between -1 and 1. Okay, because it's based on the geometric. That means that's good. Please, yeah, please make sure that you can recognize the formula. This one has, I can also force it, no alternation, starting from 0, n factorial and quantity 1/2 to the n, but it's n factorial. Let's come back. N factorial and x to the power of n, e to the power of x, e to the power of that number, 1/2 square root of e. Okay, and the first one is interesting because we see fraction, but no factorials, no n on its own. But what we can see, we definitely see something. I see -1 to the n. I see 8 to the n. I see 9 to the n times 3. Because this will be 3 to the power of 2n times 3 to the power of 1. And I can combine all of the quantities raised to the power of n, -8 over 9 to the power of n, and then 1/3. And we may recognize that this is the, 1/3 can be even placed here. Yes, we can multiply, but the entire series, infinite series, is just x to the power of n, x to the power of n. Okay, 1/3. Let me maybe divide this. Okay, x to the power of n, and this is, copy that 1/3, 1 over 1 minus x. Yes, let's come back. We can see if it's x, the entire quantity to the power of n, this is the rational function, 1 over 1 minus x. Okay, only of course if x is between -1 and 1. That means now let's actually check. Let's check if I can use, because then I can over 1 minus, and yes, if 8 over 9, it's correct. It's between -1 and 1. I can play this, and also keeping that third. Maybe I can calculate 1/3. And this will be 1 plus 8 over 9, multiplying everything by 3 and 9, maybe. This will be 9 plus 8. Or you can use different. 9 over 17, I believe so. Because this will be 17 over 9 and divided. Oh, no. Multiplying one mistake. No, that was correct, but still 1/3. That means this will be 3. That's correct because I multiply by 9. Okay, 3 over 17 is the final answer.